Hi, grade 12s. This lesson is about energy changes in chemical and nuclear reactions. And as explained on Friday, this lesson is actually the first lesson in our new unit. So our new unit, Unit 3, is about energy changes and rates of reaction. And in our first lesson, in this video, we're basically going to start thinking about what's happening with the energy in chemical reactions as well as nuclear reactions. Now, the reason why there's a picture in the opening slide of this PowerPoint of a city at night is because energy is very important in modern life. If you look at this picture, you'll see that there are lots of lights in the city landscape. In order to power all of those lights, you need energy. And where is that energy coming from? Well, in Ontario, that energy is coming from a variety of sources, but worldwide, much of the energy that we use ultimately comes from burning fossil fuels. This is the reading that was attached to today's material, and before watching this video, I would like for you to go through this reading. This reading is a lightly edited excerpt from a book called Sapiens: A Brief History of Humankind by Yuval Noah Harari. The book Sapiens is actually a very popular book that you might well have seen before in bookstores. If you've ever looked in the science section or history section of a bookstore. Sapiens is a very good book. It's one of my favorite books. As the title suggests, it basically provides an overview of the history of humankind. And it's really kind of big picture. So it starts all the way back from when the human species evolved from other species before it, about 200,000 years ago, all the way up to today. And this excerpt talks about the Industrial Revolution. The reason why this excerpt is lightly edited is because I changed things around a bit so that the opening sentence in this excerpt says, "At heart, the Industrial Revolution has been a revolution in energy conversion." Originally, that sentence was at the end of the excerpt, but I wanted to put it at the start because that's really the central idea in this reading. And that's kind of a central idea that I would like you to understand from today's material. The Industrial Revolution took place about 200 years ago. And it was basically a time in human history when we moved from doing things by hand to doing things with machines. And so that allowed us to complete tasks much more efficiently than had been possible previously. So previously, most people lived on farms, but today most people do not live on farms. And that transition has taken place because we're able to create goods and manufacture things much more efficiently than we had been able to do previously. And as the reading explains, the Industrial Revolution was really a revolution in energy conversion. So what took place in the Industrial Revolution basically is humanity figured out how to harness the energy from fossil fuels. And we figured out how to make that energy do useful things for us. So yes, there are just a couple of slides about this in today's PowerPoint. The Industrial Revolution really was a revolution in energy conversion. In the Industrial Revolution, humanity powered steam engines by burning coal. So this is a picture of coal. Coal is a fossil fuel. It's made up of the remains of dead organisms from millions of years ago. Whenever you burn coal, there's a lot of energy released. And in the Industrial Revolution, people figured out how to harness that released energy to power steam engines. And steam engines were used to manufacture and transport goods. So we figured out how to do this about 200 years ago. And since we're now able to manufacture and transport goods much more efficiently than had been possible previously, the population over the world of humans has really expanded a lot. Before 200 years ago, there wasn't nearly as many people on Earth as there is today. And that's largely because we've been able to harness the energy from coal and other fossil fuels to do useful things for us. So yes, vast amounts of energy are needed to power our modern civilization. This is another picture of a city, Ottawa. Lots of lights in this picture. Energy is needed to power these lights. As I record this video, energy is needed to run the laptop that I'm using. You need a lot of energy to power modern civilization, and most of this energy today still comes from burning coal and other fossil fuels worldwide. I did include a graph in today's PowerPoint that shows global primary energy consumption by source. This graph is taken from a website called Our World in Data. I don't honestly know if I've told you before about this website, but just in case I haven't, I'll just say a word about it. It's very cool. If you haven't ever gone to the site Our World in Data, I really would recommend that you check it out. Our World in Data is a website that basically provides data, worldwide data, about basically any topic that you could really care about. I was able to find this graph on energy consumption by source from this Our World in Data site. There's just countless graphs about a variety of topics on the website. So if you're, kind of a nerd like me and you just find data interesting, I would recommend just checking it out sometime. It's kind of cool. Now, the reason why I included this graph in our PowerPoint is because it clearly shows that even today, most of the energy that we use actually comes from fossil fuels still. So traditional biomass is this kind of dark red colored part of the graph. And you can see that for most of human history, really, traditional biomass has been our source of energy. So what is traditional biomass? It's just things like wood or charcoal. Before the Industrial Revolution, if you wanted to heat your home or cook food, you burned wood. Okay, and wood is still burned today to provide energy for people. Worldwide, people still heat their homes with wood. You perhaps heat your home with wood. But you can see, beginning about 200 years ago, we started also using coal as an energy source, and oil, and natural gas. These are all fossil fuels. Coal, oil, and natural gas are all fossil fuels. So to be clear, most of the energy that we use today still comes from fossil fuels. There's a lot of talk about moving away from fossil fuels towards more renewable sources of energy. But most of the energy today still comes from these non-renewable fossil fuel sources. Okay, but you can see, of course, there are some renewable sources of energy on the graph as well. things like hydropower, so using water to provide energy, wind, solar. These are all renewable sources of energy. Nuclear energy is shown in red, and we actually get a lot of our energy in Ontario from nuclear energy. We have some nuclear power plants in Ontario. CNL was actually a very important organization in developing a lot of these nuclear power plants. In those days, it was AECL, Atomic Energy of Canada Limited, and they did a lot of research that was needed to get the nuclear power plants in Ontario running. So yes, most of the energy that we use today still comes from fossil fuels. Okay, so in this lesson, we're basically going to talk about energy. Whenever you burn a fossil fuel, energy is released. And so we're going to, in this lesson, just think more carefully about where that energy is coming from exactly. That brings us to the idea of the law of conservation of energy. Those of you that have taken physics will likely be very familiar with this idea. It's a central idea that comes up a lot in physics and that we use to solve physics problems. So the law of conservation of energy states basically that energy cannot be created or destroyed. It can only be converted from one form to another. Whenever you turn on a light bulb at home, there is energy being released from that light bulb in the form of light energy and perhaps some heat energy. The law of conservation of energy says that this light and heat energy is not being created. What's happening is that there is instead an energy conversion from one form to another. So in the case of this light bulb, electrical energy is being converted into the light and heat energy. The reading talks a bit about how useful electricity is in our day-to-day lives. The reason why electrical energy is so useful is because it can be converted into a variety of other types of energy. So whenever you turn on a light bulb, electrical energy is being converted into light energy. Whenever you use a toaster, electrical energy is being converted into heat energy to cook the food. Whenever you turn on a fan, electrical energy is being converted into kinetic energy, which is the energy of motion. So whenever the fan moves, it has kinetic energy, the energy of motion. So electrical energy can be converted into a variety of other types of energy. And that's the law of conservation of energy at work. We're not creating energy whenever you turn on a light bulb or use a toaster or turn on a fan. What's happening instead is you're just converting from one form of energy to another. So you're converting from electrical energy into these other forms of energy. Now, this is a chemistry class, of course, so we're going to try and better understand the energy conversions that take place in chemical reactions. So let's consider what happens then when methane, which is a fossil fuel, burns. Okay, we've said that to power modern civilization, you need energy, and that energy comes from burning fossil fuels. Lots of energy is released when fossil fuels burn. But where exactly is that energy coming from? According to the law of conservation of energy, energy is not created whenever you burn a fossil fuel. Energy can only be converted from one form to another. So if there's energy being released from the burning of this methane, where is that energy coming from, right? There's energy being released here in the form of heat and light. Where did that heat and light energy come from? Well, to answer that question, we're going to think carefully about what's really happening in this chemical reaction. So this slide shows the chemical equation for the combustion of methane. When methane combusts, one molecule of methane reacts with 2 molecules of oxygen, and 1 molecule of carbon dioxide is formed along with 2 molecules of water, H2O. Now, in any chemical reaction, including this combustion of methane reaction, chemical bonds are broken in the reactants, and then new chemical bonds are formed to make the products. Okay, that's really what the definition is of a chemical reaction, really. Some chemical bonds are broken in the reactants, and then new chemical bonds are formed to make the products. And so the overall result is that the atoms get rearranged. So you have products that are chemically different from the reactants. Now, any time that you break a chemical bond, energy is required. It always requires energy to break a chemical bond. On the other hand, energy is always released whenever chemical bonds are formed. Always. The reason why these ideas are highlighted in bold is because this is an important idea that we'll be coming back to later in this unit. So the idea is important, and it's also an idea that I think a lot of students don't really fully understand. It's a common misconception for people to think that energy is released whenever chemical bonds are broken. This slide shows a picture of a fuel of some kind burning. Why is energy released whenever the fuel burns? Well, a common explanation that people often give is that energy is released when the fuel burns, because when the fuel burns, chemical bonds are broken as the fuel gets broken down. So a lot of people would say that the energy is released from the breaking down of the fuel, suggesting that energy is actually released whenever chemical bonds are broken. But this is not the case. Okay? Breaking chemical bonds always requires energy, and forming chemical bonds always releases energy. Okay, so do keep that in mind. We're going to return to this idea later in the unit, but this is important, and I hope that students leave this course understanding the ideas in bold here. Okay, so whenever methane combusts, energy is released to its surroundings. So that suggests that more energy is actually released from the formation of new bonds in the products than is required to break the bonds in the reactants. And that idea is shown in this image. To understand this idea, it's kind of helpful to imagine the combustion of methane as taking place in 2 steps. So in the first step, we break all of the chemical bonds so that we're just left with individual isolated atoms that are not bonded to each other. And then in the second step, we form bonds between these atoms to create the products carbon dioxide and water. Now, it should be made clear that in this chemical reaction, this is not actually what happens. It's not as if all of the chemical bonds get broken so that you have individual atoms and then the atoms bond to make the products. It's more complicated than that. Basically, you start out with methane and oxygen molecules, and whenever they are heated, they move around and start bumping into each other. And if they bump into each other with the right energy and the right orientation, then the products can form in that way. So it's not really that all of the chemical bonds get broken to make individual atoms, and then these individual atoms bond to form the products. But it can be helpful to imagine the combustion of methane as taking place in this way. In order to get from the reactants to these individual atoms, energy needs to be supplied. So it requires energy to break all of the bonds. But then whenever chemical bonds are formed to make the products, even more energy gets released. So more energy is released from the formation of new bonds in the products than is required to break the bonds in the reactants. And that is why the combustion of methane releases energy to its surroundings overall. So you get more energy back from forming bonds than was put into the breaking of the bonds. Now, the reason why more energy is released when the bonds in the products form than when the bonds in the reactants break is because the products have stronger bonds on average than the reactants. So this slide shows the reactants and products visually. And in the products, you can see that we have carbon-oxygen bonds, as well as hydrogen-oxygen bonds. So these bonds, on average, are actually stronger than the bonds in our reactants. The bonds in our reactants being carbon-hydrogen bonds and oxygen-oxygen bonds. So if these bonds are stronger in the products, that means that more energy is released when the products form than when the reactants break. Okay, and so the bonds in the reactants are weak by comparison, so it doesn't require as much energy to break these bonds as was released whenever these stronger bonds formed. Okay, remember that energy is always released whenever bonds form. If you're forming strong bonds, then even more energy gets released. So the stronger the bond that forms, the more energy gets released. All right, and then that brings us to the idea of potential energy, which again is an idea that those of you who have taken physics might be somewhat familiar with. So technically, potential energy is the energy of a body or system due to its position or composition. That is technically what potential energy is in chemistry and physics. To make this idea clearer, we again have an image showing the reactants and products in our chemical reaction. And the reason why we're looking at the reactants and products visually here is to just make very clear that the only difference between the reactants and products is how the atoms are arranged. We have the same atoms in both sides of this chemical reaction. So on the reactant side, we have one carbon atom. On the product side, we also have one carbon. Reactant side has 4 hydrogens. product side has 4 hydrogens. Okay, and then reactant side has 4 oxygens, product side has 4 oxygens. So the reactants and products in a chemical reaction always consist of the same atoms. You're not creating or destroying atoms in a chemical reaction. You're only rearranging them. The only difference is how the atoms are arranged. So in the reactants, the atoms are arranged differently than in the products. And so they have different potential energies. So potential energy is the energy of a body or system due to its position or composition. We have different compositions in the reactants and products, so they have different potential energies. Now, in the combustion of methane, the products have less potential energy than the reactants. So what takes place, essentially, is we start out with reactants that have a higher potential energy than the products. So in the course of the reaction, we lose potential energy. We go from a higher potential energy system to a lower potential energy system. And the potential energy that is lost in the reaction is converted into light energy and heat energy. And so that idea is shown in this image. You can see that we have a delta EP. This means change in potential energy. So the E stands for energy, and then the P is potential. And then the delta means change in. So we have a change in potential energy in going from our reactants to our products. Potential energy is lost in this reaction, and that potential energy that is lost is converted into light and thermal energy that gets released to the surroundings. Now, there's a few slides in this PowerPoint that just provide definitions of different terms that we'll be using in this unit. We've used the term surrounding already in this lesson. And so we're going to use this surrounding term throughout the unit, as well as the term system. So to provide some definitions of these terms, the system just basically refers to the reactants and products in a particular reaction. And then the surroundings is all of the matter that is not part of the system. Okay, so if we think about the combustion of methane, the system would refer to the reactants and products. So methane, oxygen, carbon dioxide, and water. In the course of the chemical reaction, when methane combusts, light and heat energy gets released to the surroundings. So if you were near this burner, you would actually feel the heat energy and you would see the light energy. So you are absorbing the heat energy and observing the light energy. You are part of the system, part of the surroundings rather. So the heat and light energy is being released onto you. Now there's different types of systems that we're going to look at in this unit. And so we're going to be using these terms throughout the unit. An open system is a system that can exchange energy and matter with its surroundings. An example of an open system would be if you were boiling, these might be eggs, I suppose, in a pot with the lid open. This system is exchanging energy and matter with its surroundings. So you can see that we are heating the eggs. Matter is being released to the surroundings because as the egg boils, steam is being released into the surroundings. And there's also an exchange of energy taking place because energy is being supplied to our system from the element that's heating the pot. So energy is being exchanged here because heat energy is being supplied to the system from the surroundings. And matter is also being exchanged because steam is being released into the surroundings. Now, a closed system can exchange energy but not matter with its surroundings. So here we've put a lid over our pot. This would be a pressure cooker, I suppose. So steam is no longer being released into the environment or into the surroundings. So there is no exchange of matter taking place between the system and its surroundings. But energy is still being exchanged. So we're still supplying energy to our system from the surroundings. Now, an isolated system, on the other hand, cannot exchange energy or matter with its surroundings. So if we put our boiling pot into an insulated container that was completely closed and did not let any heat or matter escape, that would be an isolated system. So here we're not exchanging any energy or matter with the surroundings. Okay, so we're going to be using these concepts in this unit. Oops, sorry. There we go. Now, another term that's going to come up in this unit are the terms exothermic and endothermic reactions. We looked in this lesson at the reaction that involves the combustion of methane. This is an example of an exothermic reaction. So an exothermic reaction is a reaction that releases energy to its surroundings. Whenever you combust methane, the reaction releases energy to the surroundings. That energy is released in the form of light and heat energy. Now, an endothermic reaction can also happen. An endothermic reaction, by contrast, is a reaction that absorbs energy from the surroundings. An example of such a reaction is shown in this slide. If you react nitrogen with oxygen to make nitrogen monoxide, that is actually an endothermic reaction. So that reaction absorbs energy from the surroundings. And so in these sorts of reactions, heat and light energy is not released. Energy actually needs to be absorbed. And so in an exothermic reaction like the combustion of methane, heat energy is released. And so that means that heat is given off from the reaction. In an endothermic reaction, heat is absorbed. And so that means that the reaction actually takes in heat from its surroundings. Okay, now there are just a few slides in the PowerPoint about nuclear energy as well. I know that this has been kind of a long lesson, and this video has been kind of long. I anticipated that it would be. So that's why I'm saying that this part of the PowerPoint is just for your interest. Okay, nuclear energy actually doesn't really come up later in this unit. But nuclear energy is very important, and as explained in these remaining few slides, it might well play a very important role in providing energy in the future, if scientists manage to successfully build a nuclear fusion reactor. So, since this is a long video, you don't need to worry about this material on nuclear energy. It doesn't come up later in the unit. So if you've had enough, you're welcome to just stop watching the video. But I am going to just spend a few minutes explaining this stuff because I think it's interesting, it is important, and it's also quite physicsy. And I've shared before that I quite like physics. So we'll talk just a bit about nuclear energy, and then that will be the end of the lesson. So nuclear reactions are reactions that involve the nucleus of atoms. And this is quite different from the reactions that we've seen so far in the PowerPoint. In the reactions in this PowerPoint that we've seen so far, all that we've done is just broken and formed chemical bonds. Now, chemical bonds are formed when electrons are transferred or shared between atoms. So really, in this chemical reaction, there's just electrons moving around. That's what every chemical reaction is all about. It's all about moving electrons. Nuclear reactions are different though. In nuclear reactions, the nucleus of an atom is involved. And in particular, there are two types of nuclear reactions. There are what we call fission reactions, and we're also going to see fusion reactions in this lesson as well. So fission reactions are nuclear reactions that split atoms' nuclei apart. An example of such a reaction is shown on this slide. We have ourselves a uranium-235 nucleus. I'll just zoom in here. So this is a uranium-235 nucleus. I'll just take a minute to remind ourselves of how this isotope notation works. So this is the isotope notation for the uranium-235 isotope. So the U is telling us that this is uranium. This number at the bottom left, 92, is the atomic number. So this tells us how many protons are in the nucleus of this atom. And then this 235 number at the top left is the mass number. So this number is the sum of the number of protons and neutrons. So for this atom, if you add up the number of protons and neutrons, the total comes out to be 235. That's really big. That's an enormous nucleus. So this is a uranium-235 nucleus. It turns out that if you fire a neutron at this nucleus, you get a uranium-236 nucleus. And that nucleus is unstable. It immediately falls apart into these pieces. One is a krypton nucleus, and the other is a barium nucleus. And what's interesting about this reaction is neutrons are also the products of this reaction. So whenever a uranium-236 nucleus falls apart, you get the krypton and barium nuclei, but neutrons are also released. And so these neutrons that are released in the reaction can then be used to bombard another uranium-235 nucleus And so if that other uranium-235 nucleus absorbs a neutron, then it will fall apart, thereby releasing neutrons that can then hit into other uranium-235 nuclei, and you have what we call a chain reaction. So this is actually the reaction that is used in nuclear reactors as well as in nuclear bombs. So it's a chain reaction. Basically, when one nucleus falls apart, it causes another nucleus to fall apart, which causes another nucleus to fall apart. And every time that a nucleus falls apart, there's a lot of energy released. And so that's why there are enormous amounts of energy released in nuclear power plants and in nuclear bombs. Now, this slide shows the binding energy versus the mass number for a variety of isotopes. So I'll just spend some time explaining what this chart is all about. The binding energy is basically a measure of how stable a nucleus is. So we won't get too deep into any nuclear physics in this lesson. But basically, the higher the binding energy of a nucleus, the more stable it is. Now, you can see that if you plot the binding energy over the mass number, you get an interesting shaped graph. It rises sharply and then it kind of falls off at the end here. Now, just to be clear, on the x-axis we have the mass number. So the mass number is the sum of the number of protons and neutrons. If I just go back a slide. In our uranium-235 nucleus, the mass number was 235. So the mass number is found just by adding the number of protons and neutrons. Okay, and technically, protons and neutrons are both nucleons. So nucleons is the term for the particles that are found in the nucleus. So protons are nucleons, and neutrons are also nucleons. So the mass number is really technically the number of nucleons in the atom. Now, what's interesting about this graph is that it has its highest value when the mass number is 56. Atoms that have a mass number of 56 are iron atoms. So it turns out that the iron 56 isotope is actually the most stable isotope there is. It's very, very stable. And any isotopes that have mass numbers greater than iron 56 are less stable. And any isotopes that have mass numbers less than 56 are also less stable. So iron 56 is the most stable isotope there is. Now, this is why whenever a uranium-236 nucleus falls apart, energy is released. Uranium-236 would have a mass number way towards the right end of this graph. And so when a uranium-236 nucleus falls apart, you start out with an isotope that has a mass number of 236, and then you end up with products that have mass numbers of 92 and 141. So the reactants are towards the right side of this graph, and the products are kind of more in this region of the graph. So we're going from reactants that are less stable to products that are more stable. And so since the products are more stable, they have less potential energy, and so that means that energy is released in the overall reaction. If you go from products that are less stable, if you go from reactants that are less stable to products that are more stable, energy is released. Now, the reason why I show this graph is because this graph shows that you can get energy from nuclear reactions that involve heavy nuclei falling apart into lighter ones. But you can also get energy from nuclear reactions that involve fusing lighter elements into heavier ones as well. So if you start out with isotopes that are very light towards the left side of this graph, and then fuse them together into heavier isotopes, you are creating more stable products in that reaction. And so energy gets released in those reactions as well. And so that brings us to the idea of fusion reactions. So fusion reactions are kind of the opposite of fission reactions. They are nuclear reactions that involve fusing atoms together instead of splitting atoms apart. Fusion reactions take place between very light elements like hydrogen. Hydrogen is a very light element, and whenever you fuse hydrogen atoms together, you get helium. And a lot of energy is released in this nuclear reaction. You can actually see in our graph that it rises very sharply. So that means that whenever you fuse lighter elements together, you get lots of energy. More energy than you would get from splitting apart heavier nuclei. So this nuclear reaction, shown in this slide, is the reaction between two hydrogen atoms to create helium. So here we're fusing two hydrogen atoms to create helium. This is actually the reaction that powers our sun. So our sun is just basically a giant ball of hydrogen, and in the core of our sun, the temperatures are hot enough that helium atoms fuse together, or hydrogen atoms fuse together into helium atoms. And then energy gets released in the process. This is why so much energy is released from our sun. Now, ever since scientists worked out that these fusion reactions are powering our sun, they have tried to build a fusion reactor. So all of the nuclear reactors that we have today are fission reactors that involve splitting atoms apart. And these reactors release a lot of energy, but the downside to them is that they use uranium as a fuel, which is not very easy to obtain. And whenever you split uranium atoms apart, you get these radioactive products. So you get radioactive waste from these fission reactors, which is also not ideal. So there's a worldwide effort right now, very active area of research, to try and develop a fusion reactor that uses fusion reactions instead of fission reactions. The reason why this would be a real game changer in the world of energy production is because it would use fuel that is very readily available. You would just use hydrogen that could be provided from water. There's lots of hydrogen in water, so you could use that hydrogen as fuel. And you don't get any radioactive waste. The product of the reaction is helium, which is not a radioactive product. So scientists have been working very hard to try and build a fusion reactor that can successfully fuse hydrogen into helium, so that we can make use of the energy that's released. It should be made clear, though, that this is really not a straightforward thing to do. The reason why this is so difficult is because hydrogen atoms will only fuse together if they are really, 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 really hot. Whenever you heat something up, you are giving the particles some energy to move around. And so to fuse hydrogen atoms together, you need to give the hydrogen atoms a lot of energy to move around, because the nuclei of the hydrogen atoms repel each other. So remember that like charges repel. The nuclei of hydrogen atoms are positively charged, so they are going to repel each other. The only way that you can get them to fuse together is if you get them moving around really, really, really quickly. If you get them moving around quickly, then they can overcome their forces of repulsion and fuse together. And then when they fuse together, a lot of energy gets released. Okay, so basically in these fusion reactors, you need to heat up the hydrogen to enormously high temperatures, like we're talking 150 million degrees Celsius, like hotter than in the center of our sun. And this is no easy task. It is not easy to heat up hydrogen to temperatures this high. So it really requires a lot of energy to heat up the fuel to that temperature. But the idea is that if we manage to successfully heat up the fuel to that temperature, then nuclear fusion reactions will take place and lots of energy will get released. And so more energy will get released from the fusion reaction than we put into it to get it started. Now, this YouTube video is called "Can this $22 billion mega project make nuclear fusion power a reality?" Since this material is just for your interest, I'm not saying that you have to watch this video, but I would recommend that you do watch it. It's about 11 minutes long, and it's a CNBC video. I felt that it did a good job of just summarizing the current state of nuclear fusion reactor research. There are many scientists around the world that are working very hard to get a working nuclear fusion reactor. That really would be a complete game changer in the world of energy production. It really could potentially save all of our energy production problems. It could move us away from fossil fuels towards a method of energy production that is truly sustainable, like that we could really make use of for hundreds of years. So I would recommend that you give this video a watch. Okay, there are a couple of textbook questions with this lesson. So you can spend the remainder of the period just working on those textbook questions. I know this was a long lesson, but I quite like this stuff. So I would ask at this point if there are any questions, but this is a pre-recorded video, so I can't really take questions right now. But if there are any questions about the material, feel free to reach out. Otherwise, I'll let you go, and I hope that you have a good rest of your day.